This is the solution to Advanced Calculus 2, the tutorial questions on Euler's theorem, and we're going to look specifically at question 5. The first part of question 5 gives us a complex number written as an exponential, and we're asked to express it in trigonometric form, and hence show that we get 1 minus e to the I theta all squared is equal to minus 4 e to the I theta sine squared theta by 2. We're going to start with the first expression, which is trying to express e to the minus I theta by 2, take away e to the I theta by 2, solely in terms of trigonometric expressions. Before we start, we need to recall Euler's theorem, which states that e to the I x is equal to cos x plus I sine x. We're going to use this to express both parts of the complex number which involve the exponential solely in terms of coses and sines. So doing this, we have e to the minus I theta by 2 take away e to the I theta by 2 is equal to, and then the first bracket, cos theta by 2 minus I sine theta by 2, is a result of using Euler's theorem on the expression e to the minus I theta by 2. The second expression is similarly a result of using Euler's theorem on e to the I theta by 2. We can now simplify this expression and get minus 2i sine theta by 2. You should be able to see that the cos terms cancel out and we get 2 minuses on the I sine theta by 2 term. So this is expressed, that particular exponential form, in terms of trigonometric functions. Next, we're asked to deal with this particular term, 1 minus e to the I theta all squared. And here we've simply expanded the brackets out. And again, we have e to the I theta and e to the I 2 theta. And we can use Euler's theorem to rewrite both of those exponential forms of complex numbers. For the next part, we need to remember our trigonometric relationships for cos 2 theta and sine 2 theta. We have the following. Cos 2 theta is equal to 2 cos squared theta minus 1. Cos 2 theta is 1 minus 2 sine squared theta, and the one that's easiest to remember is sine 2 theta is equal to 2 sine theta cos theta. These were done at level 1 when you were doing core techniques. Using these expressions, we have the 1 plus cos 2 theta can be rewritten as 2 cos squared theta, and similarly the sine 2 theta term can be written as 2 sine theta cos theta. Now what I'm going to do is I'm going to factorise the last two expressions, taking out the common factor of 2 and cos theta. We can now factorise again. We have a common factor of 2 cos theta plus I sine theta. So taking this out as a common factor gives us 2 cos theta plus I sine theta, and then the final bracket is minus 1 plus cos theta. Now, the reason we happen to use the form of cos 2 theta that we've got is because the end result requires us to have a cos theta plus I sine theta term on its own. If we look at the final expression, we want an e to the I theta, which is the same as having a cos theta plus I sine theta. So now I can use Euler's theorem, and that replaces the cos theta plus I sine theta with an e to the I theta. The next expression may look very strange. We've got a minus 1 plus cos theta. Now, if we look at the second expression for cos 2 theta, that is cos 2 theta is equal to 1 minus sine 2 sine squared theta, if I basically replace the 2 theta with just a theta, I will get cos theta is equal to 1 minus 2 sine squared theta by 2. And using this simplifies minus 1 plus cos theta to minus 2 sine squared theta by 2. And finally simplifying that expression gives me the required minus 4 e to the I theta sine squared theta by 2. Now, that's done the first part of the question. We'll use this later on. Now it says, the second part, for a positive integer n, we've defined two series, c and s. And here, the 2nj, well, is 2n choose j, is just the binomial coefficient. We're asked to consider expansion of 1 minus y to the power of 2m and show that we get the resulting expression for c and find a similar expression for s. The first thing I'm going to do is write down the binomial expansion of 1 minus y to the power of 2m. The reason we're doing the binomial expansion is, 1, the question mentions the binomial coefficient, 2, it also says consider that expansion. Now, we certainly have something that looks very similar to the expressions for c and s above. The only difference is the binomial expansion has powers of y in it. The next step is, again, relying on our understanding of Euler's theorem. We're going to compute c plus is. The reason for that is if you look at the cos and sine terms on the c and s expression, they pair up. And now we have cos theta plus I sine theta, a cos 2 theta plus I sine 2 theta, and so on and so forth. Those terms we can use Euler's theorem once more again on to get c plus is is equal to 1 minus 2n choose 1 e to the I theta, 2n choose 2 e to the 2 I theta, and so on and so forth. And now we should be able to see, comparing our expression for c plus is and the expansion we have for 1 minus y to the 2n, that if we let y equal e to the I theta, then the two expressions will be the same. So that implies that c plus is is simply equal to 1 minus e to the I theta all to the power of 2m. Hence, we've managed to create a great simplification of the original expression. Now, we need to, if we're going to work out an expression for c and an expression for s, compute the real and imaginary parts of 1 minus e to the I theta to the power of 2m. And to use that, we need to use the result we developed in part A. So this is the expression we've got. Part A tells us that 1 minus e to the I theta all squared is equal to minus 4 e to the I theta sine squared theta by 2. Substituting that result in, we get c plus is, which is equal to 1 minus e to the I theta all to the power of 2n, is simply equal to minus 4 e to the I theta sine squared theta, well, theta by 2, all to the power of n. Expanding that out, we get the minus 4 to the n, e to the in theta, sine to the 2n, theta by 2. And again, using Euler's theorem, gives us this particular result.